A key parameter in determining the actual risk of a gas to ignite is the mixture reaching its flammability limits in air. The lower flammability limit is important as you need to have enough gas mixed with air in order for it to reach its flammable concentrations to ignite and burn. So if during a leak situation, the leak rate and the quantity released is large enough that it surpasses the lower flammability limit, flammable concentrations can form. Propane is a commonly used low GWP refrigerant in small refrigerated cabinets, but its lower flammability limit is only 2% propane by volume in air. This means that for even small charge sizes, flammable layers can form and actually ignite and burn. You typically need 4 times more A2Ls to reach flammable concentrations as compared to A3s such as propane. Hence, A2Ls are inherently safer as you're less likely to form flammable concentrations. This means much higher quantities of low GWP A2L refrigerants are necessary just to be flammable, which means there are a number of leak scenarios for these A2Ls that would not even result in any consequential flammable volumes. Another key parameter in determining whether a mixture actually ignites or doesn't ignite is the minimum ignition energy, or the MIE. The minimum ignition energy is important as most electrical components actually can produce electrical sparks under normal operation, unless they're specifically designed to actually avoid that. If the energy of the spark or the electrical discharge is higher than the minimum ignition energy, then in a specific leak scenario, you can actually ignite the mixture if flammable concentrations are reached. Propane has a minimum ignition energy of just 0.25 millijoules, which means that even a weak discharge, static discharge, say from your clothing, can actually exceed this value and potentially cause an ignition event. To give you an idea of what millijoules are, so say for example in the wintertime, I'm actually shuffling my feet on the carpet and I actually touch a door handle and I actually shock myself, that value is actually 20 millijoules, or almost 100 times higher than the energy necessary to ignite propane. In comparison, A2L refrigerants have minimum ignition values 2,000 times higher than that of propane, meaning much higher energy sources are required in order to obtain ignition. This also means that many commonly used electronic components can be used safely with Opteon XL refrigerants. The severity of an accidental ignition can be determined by many factors, such as reactivity, for example, how fast the flame burns, or burning velocity, as well as combustion energy. The higher the gas's reactivity and combustion energy, the larger the potential impact the accident can have on the surrounding area. To put that into perspective, the combustion energy of Opteon XL20 is approximately 5 times lower than that of propane. In addition, it's significantly less reactive than propane, where its burning velocity is actually 30 times slower. When a combination of factors occur, for example, a leakage that can result in sufficient flammable concentration, plus an ignition source that can easily ignite a highly reactive refrigerant with a low MIE, that can result in a fire, rapid flame propagation, and even an explosion. A2Ls are less likely to form flammable concentrations, allowing for larger charge sizes for a larger application range. A2Ls are harder to ignite, making them safer to use with many commonly used electronic components. A2Ls are less reactive and have a lower combustion energy. Hence, A2Ls generate lower severity ignition events. Given these factors, A2L refrigerants can be considered an inherently safer solution than A3s, such as propane.